Hello and a very warm welcome to all of you. My name is Thorsten Lenk. I'm the Program Lead International Energy Data and Modeling Hub at Agora Think Tanks. Welcome to today's webinar, Behind the Scene Features and Functions of the Locational Agorameter. We are really happy you could join us today, whether you are here out of sheer curiosity, deep technical interest, or just because you couldn't resist another webinar about electrical prices. After our first session on April 13th, where we introduced our study and our new web tool on locational electricity prices in Germany, the Locational Agorameter, today we are shifting gears a bit. This time it's all about what's under the hood, the data, the modeling, and the setup that make the tool work. Over the next around 90 minutes, we will start by briefly revisiting the key findings of the study with my colleague Katharina Harz from the German Power team. Then Kaspar Knorr will walk us through the modeling approach, and we will see how the Gurobi solver helps us tackle the optimization challenge with Frank Hager, Director Energy from Gurobi. Together with my colleague Gia Loy, we also take a deeper look at the tool's features, the software used, and the development of the tool. Feel free to drop your questions in the Q&A section at any time. Our team will do their best to answer them live. And anything that slips through will be picked up in the Q&A at the end. Before I hand over to Katharina, to get us started, I would like to take the opportunity to thank our colleagues from Fraunhofer IEE and Gurobi, and last but not least, my colleagues for the excellent cooperation over the last more than 2.5 years we had. And now, Katharina, the floor is yours.
Thank you, Thorsten. Also from my side, very warm welcome. I want to give you a quick overview over why we developed this tool and what we found out during its development. Of course, electricity prices have played a much more important role recently in the political debate, and one of the factors that keeps driving them up is redispatch costs. Due to the growing structural mismatch of concentrated renewable, mostly wind generation in the north, but more demand in the south of Germany, redispatch costs increased significantly over the last years. And although more transmission lines are planned and also being built, the TSOs have estimated that this trend in cost development will continue. But this has been an issue discussed in academia over many years now. I even remember I motivated my bachelor thesis with this redispatch cost trend. So why is it discussed now in a broader public debate? I would say mainly three things happened. Last year, many economists, many scientists reignited the debate by voicing publicly that the single bidding zone is sending wrong market signals and should be replaced by a locational pricing system. Here, we picked an example of a much noticed article in the FAZ, but there were many others, of course. Second, as many of you know, the bidding zone review was published by NSUI 2 weeks ago and found high cost savings for the 5 bidding zone configuration that they assessed, which was the highest number of zones. They also evaluated 2, 3, 4, 5 zones. And of course, this finding came with many conditions in this report. So it was not a clear recommendation for split it to 5 zones, but it emphasized at least the economic welfare advantage of splitting zones. And third, the governing parties did anticipate the publication of the bidding zone review and maybe even that it would emphasize the economic advantage of transforming the single bidding zone. Now, the coalition treaty states that the single bidding zone should not be touched, but during the negotiations, we saw that the Social Democrats, at least, would be open for this debate. And of course, for the first time, this topic was discussed on the federal level among the most influential politicians. Now, after this overview over the debate in Germany, let's have a look at what we did to contribute recommendations to the discussion. Together with our colleagues from Fraunhofer IEE, we did a study on 3 different market design configurations to assess advantages and disadvantages, but also, and maybe more importantly, who would be affected and how. We simulated the single bidding zone to have a reference point, and then simulated the 3 bidding zones, also assessed in the bidding zone review, and another configuration of 22 price hubs, as you can see on the right side. These price hubs could either be interpreted as 22 small zones or 22 nodes. And the input data we used include real-world generation data from the years 2019 to 2023. So we assessed the impact that a system change would have had on the past years. This allowed us to assess the impact of one variable, the configuration, as opposed to having to figure out which change in the price comes from which assumption on future grid expansion, on future generation demand patterns, or the configuration of the bidding zones. So this was all on the study. In parallel, we also developed the web tool we are presenting today that runs the model for the 22 price hubs every day with live data to provide an always up-to-date databases, which is even more important now, I would say, as we see that the political debate has only started, and the biggest critique on the bidding zone review was actually that it is already outdated. Now, analyzing the data from the model runs for the study and live tool, we have learned a lot about the effects of local pricing, and we boiled it down to 4 key findings. First, the single bidding zone is blind to grid congestion and sends the wrong signals to market participants. Signals that often have to be corrected through redispatch measures. While this might still work today reasonably well, in many cases, these distortions are becoming increasingly problematic as more and more decentral and flexible consumers, storage, but also producers begin to align their behavior with these faulty price signals. Second, geographically, more granular electricity prices could significantly reduce the need for grid operator interventions. And one realization that comes with this finding is splitting the market into just a few large zones is not as effective as introducing more granular pricing. And moreover, it also proves very difficult, if not impossible, to find large zones that make sense over a long period of time. Third, introducing local electricity prices would actually lower electricity costs for the vast majority of consumers. And I really want to emphasize vast majority here. This finding becomes clear when factoring in not just wholesale prices, which are only lower in the north, but also the avoided redispatch costs. This is the case because the reduced grid tariffs due to avoided redispatch costs overcompensate the higher wholesale prices in the south in most of the local price hubs. Of course, there are still some consumers and generators that may not benefit or may even be disadvantaged, and these are mainly 2 groups. First, energy-intensive industry in the south, and second, renewable producers in the north. The problem with the first group is that they wouldn't benefit from reduced redispatch costs as much as household consumers, as they are already paying reduced grid fees. That's why they would only see the higher wholesale price, but not the lower grid tariff. And the second group of producers in the north would, of course, earn less money on the market due to lower wholesale prices. Addressing those cases will be an essential part of gaining political support, and that's why we have taken these concerns into account in our study and proposed respective targeted solutions. And last but not least, a locally organized electricity market not a second market alongside the existing single bidding zone, but a truly integrated and consistent local market would significantly increase the cost efficiency of climate neutral power system. And this is also something that is supported by the findings of the bidding zone review. So even though the current coalition agreement includes a political commitment to maintain the single bidding zone, the debate around a more efficient market design will not go away, and probably even intensify with more and more flexibilities coming into the system. So we believe both science and politics need to be prepared for this debate, and that's why with our study and the ongoing data collection of the Locational Agorameter tool, we aim to provide a solid foundation to support continued in-depth analysis. And with this, I hand over to you, Caspar, for the deep dive into the details of the model.
Yeah, thank you, Katharina, for giving us insights into the political background and the key findings. Today, I will present the modeling behind the locational agorometer. Well, my name is Caspar Nohr. I'm working for the Fraunhofer Institute for Energy Economics and Energy System Technology since almost 19 years as a scientist and as a project leader. My presentation is divided into 3 parts. I will start with giving insights into the input data and the data flow. Then I will say something about the optimization models we used or we still use in live operation. And then I will finish with some words about the data processing. So let us start with the German grid. So right here you see the a model of the German extra high voltage grid. It has over 800 lines and over 500 nodes, and we need this detailed model to detect single overloaded grid components. However, we aggregate this complex model to an easier one. So we aggregate the lines and the hubs nodes to 34 lines and 22 hubs. And we do this for the purpose of result presentation and for the calculability of the electricity markets. So at the end, we simulate 22 electricity markets in Germany. But it is important to note that we still use the complete grid model in background calculations. So let's continue with the spatio-temporal resolution of the input data. One important input data is the wind power feed-in and solar power feed-in, as well as the electricity consumption of the German zip codes. We do day ahead forecasts or even 72-hour ahead forecasts for every single zip code in Germany. This is done by a Fraunhofer system. So Germany is not an island. It's placed right in the middle of Europe. And that's why we also have to take into account the power values of the neighboring countries of Germany. So we acquire or obtain actual values and forecasts of wind power, solar, electricity consumption, must-run units, net transfer capacities, as well as power plant availabilities, fuel and carbon dioxide prices for Germany and its neighboring countries. And we also obtain commercial exchanges from the satellites, which are colored blue in this map. And all this data we obtain from ENSORI transparency platform, the Agorameter, or from Montel. And all data is processed in an hourly resolution. So let us continue with an overview on the data flow. Well, the data flow is executed hourly in live operation, and we have more than 35,000 time series as input. For example, we acquire weather data, actual values and forecasts of weather data. We use geographical information data and also master data such as installed capacities or hub heights, and also market values to estimate the bids for renewable energies. And we use this data to get the regional wind power feed-in, photovoltaic feed-in, the regional consumption, and also the regional heat demand at the zip code level in Germany. And for the other countries, we acquire wind power feed-in, actual values and forecasts, as well as photovoltaics, then also power consumptions, net transfer capacities, fuel prices, and carbon dioxide prices, and a power plant list to localize the locations of the power plants. And as I mentioned before, we have a grid model in the background to model the input export between our regions. The core of the whole process is are two optimization models. On the one hand, it's the optimization of the grid, the power flow calculations. We use the model IEE opt for this purpose. And the other optimization model is called Scope EM. We use it for power plant dispatch or unit commitment to do the market simulation. One side product of those calculations are the emissions. But the main results are the local market prices and also the grid load. Then we transfer those results to the live Agorameter, Locational Agorameter. And we did also a study, as Katharina mentioned before. There we have some additional results and analysis, just as the redispatch demand or additional technologies like electrical mobility, heat pumps, or batteries. Well, Agora did a good job for visualizing our output data. We will see this in a later presentation by Mrs. Loy. Well, right here is a shortened version of the power flow. Again, we collect large amount of input data, clean it up, replace some missing values. I will say about this something later on, and transfer it to our two optimization models, our model Scope EM and IEE opt. And Scope EM uses the Gurobi solver, which Frank Hager will say something about in the next presentation. We did this whole process for the study for the years 2019 to 2023 to obtain parameters we will use in our live operation. So now we come to the second part of my presentation. It's about optimization models. Well, I'm not an expert in optimization, so I will keep it short. If you have detailed questions about this, you can post those questions later in the Q&A session. The first model is the Scope EM. It solves unit commitment and economic dispatch problems. On the left side, we see the input data I showed on the last slides. This input data is transformed to the solver with the objective of minimizing the system operation costs. We use a rolling planning horizon inside the optimization. It's a 48 hours planning horizon in the case of the locational agorameter. The output is then optimized power sector unit schedules also, and power market prices and much more. And below you see the markets we model. It's the wholesale markets, the day ahead markets in case of the locational agorameter, but Scope EM is also able to optimize intraday auction market or the balancing market. The second optimization model is the IEE opt, which is used to do the redispatch optimization. Well, here are some equations given. So the objective function is to minimize the redispatch costs. And we have a lot of constraints which are taken into account by the optimization. A detailed description of the methodology is given in a publication, which is denoted in the footnote below. So let us come to the last section. It's about data processing. And let us start with the availability of NSOE actual data. So we observed, we used a period from last year, September, to get those results. We can see that from now, if we look back into the past, if we look 1 hour back into the past, we see that not all data is given. If we look 2 hours back into the past, then we see almost all data is given by NSOE. And 3 hours from now in the past, all data is available on the transparency platform. On this slide, we take a look on the forecast horizons of NSOE forecasts. So for example, at 12 o'clock, some data of NSOE has only a forecast horizon of 10 hours. Other have a forecast horizon of 34 hours. And also some data has a long forecast horizon, more than 47 hours into future. Here, these horizons or delays are shown in a different way. You can see that most NSOE forecasts reach less than 45 hours into the future. And also the delay of the actual values from NSOE is smaller than 3 hours. Now I complete this illustration by the Fraunhofer IEE forecast for German zip codes. This forecast is bigger than 48 hours. And also the Agora metadata, which is based on the actual values of NSOE, has a delay of less than 3 hours. For our unit commitment, we need an forecast horizon of 38 hours. And we have an overlap to the actual values. So in our unit commitment optimization, we always have actual values at the start of our unit commitment. But it is clear that we need some replacement values for missing NSOE forecasts. But the use of replacement values isn't very problematic for our model, because the next hours from now are the most important one for unit commitment. And also we update those values every hour. So right here we see the output data. It's the data we transfer to Agora to be visualized in Agorameter. This data reaches back to the 1st January 2019 and goes to now. and is also completed by forecasts. And at the beginning of every year, we do recalculations of the locational agorameter data. I will say something about this later. But now the next slide is about those replacement values. So to illustrate how we do replacement values, we see the consumption given by NSOE for Poland. This consumption in this example reaches 12 hours into the future, but we need a larger forecast horizon. That is why we use replacement values for the missing forecast horizon. And in the case of consumption, we use the consumption of the last day of the same type. So if it is a working day, we use the last working day, or if it is weekend or holiday, we use the last weekend or holiday to replace those missing NSOE forecasts for consumption. In the case of wind power, which is given for the example of Belgium in this case as a green line, we see that the forecast horizon of for Belgium is only given again 12 hours into the future. And to enlarge this forecast horizon, we use the scaled onshore wind power feed-in of the nearest hub, given by the red line. And doing this, we get a replacement for the missing onshore wind power feed-in of Belgium. So I come to my summary. We do an extensive preparation of validated input data, and only in case of missing input data, we need to use replacement data. We use complex optimization system in an hourly live operation. And doing so, we do have a reliable representation of a German bidding zone splitting using 22 electricity hubs, which can be interpreted as 22 small zones or an approximation of a nodal pricing system. Currently, we are finalizing scientific publication about our model. Well, you can see the title and the authors already here. I think it will be published in approximately one month. And my last point are the yearly recalculations. So at the beginning of each year, we update the grid model. We update the power plant list. We also update the Agora metadata. And we update renewable curtailments, which are published by a German agency every year. And also we will incorporate new technologies into the locational agorameter. The next new technology will be large-scale batteries. So that's it from my side. Thank you for your attention. I hand over to Frank Häger now.
All right, thank you very much. So I'm Frank Häger, Director Energy at Gorobi, and I have the honor to present the solver behind the Agorameter model. It will not be a very technical deep dive, but a high-level overview about optimization in the energy sector. And if you're interested in exploring the solver behind the model in more detail, then drop me a note and we'll arrange a technical or mathematical session. Optimization. So the task is take optimal decisions, of course, the challenge respecting business constraints. And the goal is to minimize or maximize one or even more objectives, for example, which you find in the energy trilemma, which is sustainability, security, and affordability. The solver is on a mission to find the best solution, or at least close by with the most minimum gap. It provides a proof of optimality when the model is feasible, and it serves as a technology to the rescue of many projects which would remain unresolved otherwise. So decision-making priorities, which can this be? Similar to the objective function, evaluating projects in the energy industry also requires to balance the decision-making priorities. I already mentioned the energy economic trilemma, which is the reliability and energy security, which is cost effectiveness and economic value, but also being sustainable and adhere to the environmental commitments. So if we summarize those, these address the energy economic trilemma. But then we have, of course, alignment with the German or European strategy, and this is respecting climate goals and regulations. And then we have the innovation and technological leadership paired with collaboration and partnership applied in an agile and phased approach. And that's what you're seeing here with the nodal agorameter, where basically Fraunhofer and Agora work together, but in the background, of course, there's the Agorabe optimizer and other partners involved. And all of these supports leadership, and that's what we need in order to progress quickly. A little bit digging into the past. Before 1989, mostly heuristics were applied to problems in the energy landscape. Mixed integer linear programming did exist, many models, but no real usage. In the late 1980s, the Electric Power Research Institute, EPRI, acknowledged that the potential of mixed integer linear programming for energy systems is there, but they also highlighted its complexity and the implementation challenges. At that time, a 7-day unit commitment problem could not be solved. In the same year, during DMAC's meeting, which is the Center for Discrete Mathematics and Theoretical Computer Science, Bob Bixby showed that a unit commitment model, as I said previously, running 7 days, now solved to optimality in 22 minutes. It takes 22 seconds to a day. How did he do this? Basically, the legend says that overnight he programmed the model using a pre-solve and branch and cut approach, and he presented it the other day during this meeting. And indeed, the demonstration really kicked something off. Not only in the solver development, where we can solve more than 10 million variables in minutes or seconds now, we are seeing many integrations with Python frameworks, but also we are applying multi-threading, tuning approaches, numerical stability. And background for this is, although the methodology behind is pretty much known, it's really the engineering aspect that and approach that Agorabe took in order to become industry leader for the optimization solver. So I talked about this speed up. This is a benchmark where we measure the performance on the same CPU. So in fact, and in reality, the speed up is higher. But if we had a computer available in the year 2008 today, and we still have that CPU, and you would run these models, then we see a 91 plus speed up. At the same time, the previously unsolved models were dramatically reduced by 90% approximately. So this means that the mixed integer linear programming approach is really available to many business problems now. So if we provide a little overview why optimization is significant mathematically and practically, is that these efficient mixed integer linear program formulations today reduce complexity, tighten the constraints, which is regulatory, which is prescribed from the regulations, and unlock all the solver speed. Yeah, so you are really saving time and resources and money from the start. We don't just crush numbers. It is that inside the solver, there's a lot of machine learning. Today, you probably would say artificial intelligence that help with pre-solve, LP relaxation, smart branching, and so on. This in order to keep the search tree, of course, lean and fast, and so that we can exclude the search space in which we are not supposed to find the optimal solution, but rather search in the remaining region. The exact methods are today really outperforming heuristics, and that means that in energy planning, scheduling, routing, and market design, optimization is just an industry standard. Let's put it on with a business perspective. Optimization is not just a tool today. It's really a strategic advantage to solve the problems we are facing today. And that's not only in energy, it's also in supply chain and other areas. And as you can see here, organizations in partnership like Fraunhofer, Agora, and Gorobi are modeling really better futures. It may be politically under dispute and will be argued, but basically we do have a model now and which serves us to judge the future. And with this team is solving real and relevant problems with an optimization solver at the core. Thank you very much. I keep it short, and thank you for your attention, and thanks for the invitation, and hope to have many more opportunities to partner with you and to show value with climate impact in the energy transition. Any questions at the moment?
So far, I saw no questions in the Q&A section on the optimization. If there are questions, please put it to the Q&A section, and Frank Heger tries to answer them directly in the chat. Thanks, Frank, also for the very excellent cooperation. And with that, I hand over to Gia Loy, my colleague from the data and modeling team at Agora, to see more features and the development of the locational agorameter. Gia, the floor is yours.
Thank you, Torsten. And hello, everyone. Let me share my screen. Hello, my name is Gia Loy. So I'm on the data team here at Agora. And there are 2 points on my agenda. I will first take you on a wee tour of the tool. I will talk about some of the different visualizations and how you can use this to explore locational data. And then for the second part, I will talk you through the process of how we actually designed and developed this tool. So let's switch to the tool. And now you're looking at the locational agorameter, within which we have 3 different views: a single view, a comparison view, and a hub view. I will start with a single view. So here, this shows the map of Germany with the 22 modeled hubs, as well as the neighbor countries that Germany trades with. And we are here looking at the data for power price and grid load. And these lines between the hubs, they represent the grid connections. Now, whenever a map loads, what you see visualized is the data for the very first timestamp of the selected time period. So in this case, for instance, the first hour of the 20th of February, 2025. And when you click play to play the map, you see the map and the grid animate as we move through the timestamps of the selected time period. Now, you also get some detailed information about the different hubs in the pop-ups. So when you hover over a hub, for instance, here you get information about the hub's power exchange, the import and export, and also the hub's power price, in this case, 90 euros per megawatt hour, and also the actual power price of Germany from ENSOE, which we show in pink. Now, on the price map, you also see these arrows between the hubs. These represent the power exchange. So the arrowheads, they show the overall net direction of the flow, and the darkness of the arrows represents how close the line is to the connection's capacity. So anything above 95% is defined as critical and appears as a solid black like this. If you hover over the line itself, you also get more information about the power exchange in both directions. We also have some data indicators in the legend. So here you see this D marker, which shows again the actual power price of Germany. And this bar within the legend shows the range of values for all 22 German hubs. So you get a rough indication of the spread of prices across all hubs at this point in time. And you may also have noticed these icons in the bottom right. So these icons show the capacity ratios for wind generation, power demand, and solar generation, respectively. And so essentially they provide a rough indication of how much wind and solar are being generated and how high demand is at that point in time. And this information can in turn be relevant for things like interpreting grid congestion and locational price differences. For instance, here we have a case of relatively high wind and high demand, but low PV generation. And such cases often lead to things like grid congestion because a lot of power is being transported from the north to the south. And consequently, price differences between the north and the south emerge, as we can actually see from the map here. So we get lots of green in the north, yellow in the south. Power is mainly moving towards the south, and some lines are running at capacity. All right, so hopefully that gives you an idea of how to interpret a single maps visualization. Remember, you can always select a different date or change the resolution using this date picker here. And so far, I've only talked about power price, but there are also 5 different categories of data which you can visualize, including renewable to demand ratio, total grid emissions, grid emission factor, and flexibility profit index. I will not go into all of these in detail since we've got notes explaining all of them on the maps, but feel free to also ask questions about them during the Q&A if you've got any later. So I'd like to move on to the comparison view now. Here we have 2 options, compare timeframes and compare categories. The categories option, this allows you to compare 2 different categories of data. And this view might be useful for you if you're wanting to, say, better understand the relationship between different indicators in the data. Here, for example, we know that price and renewables tend to be quite closely coupled. And indeed, we can see that as we move through the timestamps in this selected time period, areas that have a higher renewable to demand ratio, so that's the brighter green hubs in this map on the right, these also tend to be associated with lower or even negative power prices, as we can see in the map on the left. And you can also select which 2 categories you would like to compare using this menu here. So for instance, maybe renewables and emissions might be another comparison that could be meaningful to look at. For the timeframes option, this allows you to compare 2 different time periods for a single category of data. So here, for instance, we're looking at the 1st of May 2025 versus the 1st week of May that year. And you should keep in mind that the right map always shows the data aggregated across the entire time period. So say these power exchange values, for instance, they would be the total sum of imports or of exports for all hours in the 7 days for this particular hub. For the power prices, obviously, it doesn't make sense to sum these up. So we show the daily averaged value instead. And this view could be useful for you if you are wanting to look at, say, how prices on a particular day may compare with the average across a bigger period. So let's say, for instance, I'm interested in Kingston in 2023, for instance, which was around the 28th and 29th of May. And I would like to look at how this compares with the average across the month of May that year. So I can select those parameters and have a look at the chart. And here we see that we do indeed get lower prices and also more negative prices on these days compared to the daily average across that month. It's also useful to remember that you can always download the raw data behind the visualizations using the data download option here. If you would like to get a screenshot of the chart, you can use the PNG or SVG download options. I highly recommend the SVG option. This gives you a really high quality image download, which could be good for sharing on social media and so on. And finally, let's move on to the hub view. So here we move away from maps and we get a set of charts, which you might be familiar with if you use our live Agorameter. The difference is that here we show the model data for each individual hub. So this view might be useful for you if you are wanting to, say, zoom in on a particular hub of interest. Let's say I would like to look at power generation and consumption of North Sea, for example. Here we have on the x-axis, we have the time. On the y-axis, we have the values for the different power generations. This hub is in the north, so I might want to look at wind in particular. And here we see that we get a good deal of wind generation in this hub, as we might expect. Whereas let's take a look at something in the south, let's say Kinsey, for instance. And here we see that we get considerably less wind, unsurprisingly. On the other hand, we can see that we get a lot more hydro in the south, as we would expect. And in fact, this view could be quite good at looking at seasonal changes over time. So for that, let's select the entire year, for instance. And here you see how the power generation values change over the course of the last 12 months. For hydro, for example, we see the expected peak around the late spring and the early summer because of the snowmelt from the Alps, whereas we get the expected drop in the middle of the year towards the later part of the year because obviously the summer months are more dry. And notably, we don't get this same seasonal pattern if we look at some other hub in the north, for example. Now, another thing the hub view could be useful for is exploring how locational pricing plays out in different regions. In particular, it could be good for highlighting how price fluctuations may vary across different hubs. And for that, so let's select a chart which includes power price, like this one, and we want to select a single day as an example. So here we can see that in this hub on this date, power prices dip in the middle of the day around the afternoon. So let's say I had an electric car, for instance. According to this data, sometime in the afternoon might be a good time to charge my car. Whereas, however, let's take a look at a different hub. And here we see quite a different price variation over time in this hub, where we get lower prices throughout the night and in the first half of the day, and then higher prices from the afternoon onwards. So afternoon might not be such a good time to start charging my car. I might want to charge it overnight instead. And so this is just an example of how you could use the charts to explore the effects of locational pricing on users. And I think the last thing I want to mention is this fun new feature that we've just added to the tool recently, which is the changelog. And here we are publishing the version history of the Agorameter, where you can keep track of new features and updates to the tool. And the fun part is that it is interactive. So as users, you can like or dislike features in the latest release. And this is actually really helpful information for us for future development. So if you're a fan of the Locational Agorameter, please go to the changelog and let us know. Okay, now let me go back to my slides. So that concludes the tour of the tool. And for the next part, I will talk about the process of how we actually designed and developed this tool. So these are the technologies that go into the Locational Agorameter. We have a backend where we collect and store the data, and a front end where we present the data to you. On the backend, we manage the data in a Postgres database. We use Python scripts and some scheduled cron jobs to regularly fetch the data from source, clean it, and convert it to a standard format that we use in our database. And this is all work done by our lovely backend people on the data team, Paulina, Yuchi, and Long, and Said. And on the front end, we use Django to interface with this backend. So to send requests for the data. The UI of the tool itself is built in JavaScript, and for the actual data visualizations, we use d3.js and Flourish. So D3 is an open source JavaScript library for visualizing data. It makes use of standard web elements like SVGs, which you use to create your chart components. And Flourish is an online data visualization platform that you use some chart templates to create charts from. So we use D3 for the maps that you see in the tool, and Flourish for the charts you see in Hub View. Now, the process of development started with some rounds of brainstorming where we discussed things like the appearance of the tool, the behavior of the tool, so how users should interact with it, and the functionality of the tool. So what were the features that we needed? For instance, we knew we wanted pop-ups to provide information for different regions. There needed to be a way for users to select the date range and so on. And we also discussed different possibilities of visualizing the data spatially, in particular, how to highlight different regions on the map. Now, we also needed a more concrete idea of how the tool would be integrated within the environment of the Agorameter. So what you're looking at now is some Figma mockups we had created in collaboration with some of our external consultants. These basically give you an idea of how we envisioned the final version of the tool to look like in our website. And in particular, we're paying attention here to things like how the charts should appear within the UI of the tool, how users should select the different visualization options, how to present the information to them in order to make the user experience as seamless, as intuitive as possible, things like that. And obviously, these were quite early sketches. And we went on to further develop these over the course of implementation. So with more brainstorming and also some feedback from colleagues, we refined these ideas into what you actually see today. Now, to give you an idea of how the visualizations developed over time, I'd like to share with you an example of how the map evolved from the very initial time to what you see today. And a lot of this was development work done by Charlotte, our amazing student assistant on the data team. You'll see that what she started out with was actually quite different. So we started by creating the maps in Flourish. We first tried to just create a single map of Germany with some different areas colored according to some data. So we tried different versions with ovals, with circles, also with hexagons. And hexagons ended up being the clear winner. So we went on to base future development on this concept. We added the grid connection lines. We also tested varying the number of hexagons. So more hexagons obviously gives you a more fine-grained visualization, but also has the downside of being more resource intensive to render. So this was a trade-off we had to consider. To put things into perspective, the version of the maps that you see today comprise of some 1,700 hexagons each. We also tested different methods of interpolation. So this is a function which maps colors onto a numerical scale. There are different algorithms you can implement to achieve different visual effects. For instance, we tested zonal interpolation. So that's where entire regions, entire zones, these are colored according to a value. And then we implement a gradient at the border between zones. But we also tested nodal interpolation. So that's where specific nodes, and in this case, the nucleus of each hub, these are colored according to a value. And then individual hexagons are weighted based on that distance from these hubs. And that gives you a kind of sort of spreading effect from the center of all the hubs that you see in this map on the right. And we actually use both of these in the current tool. So the price map, for instance, uses zonal interpolation because this is quite good for visualizing price differences between regions, for instance, between the north and the south. Whereas the emissions map, on the other hand, uses nodal interpolation, because here we are interested in emissions at individual hubs, so it makes more sense to highlight this instead. Now, it was at this point that we realized that Flourish was too limited for what we were trying to build. It was actually impossible to implement some of the functionalities that we needed. So we decided to switch to D3 instead. And this, of course, meant we had to re-implement the maps from the beginning, but the big advantage was that D3 offered us full customizability over what we were trying to visualize, which was really good. So we first started by creating the maps again in the same style with hexagons. We then went on to create a version with a playable time slider. So I'll explain a bit more about how this works later on. We refined the overall design of the tool. So this is the first version that you are seeing that starts to somewhat resemble the tool today. And we went on to develop visualization of the power flow. This was one of the first designs we tested, which we decided was a bit too visually busy. So we tried some alternatives instead, like using solid arrows, which is a bit closer to what you see today. We went on to customize the legends. So previously, the tick values you saw in the legends, these were always fixed. They always reflected the entire data range. And this could obviously be very, very big. So we optimized this by making it dynamic. What you see now is a range that always zooms in on the current selected data period. And finally, we went on to implement the other dynamic elements you see on the page. Things like the pop-ups, the capacity ratio icons, the bar and the marker in the legend, and so on. And obviously, at the same time, we extended these to the two comparison views. So we implemented a second map, either for a different category or a different time period. So finally, we finished developing the tool and deployed it on the web. But there is, in fact, still a series of actions that takes place behind the scenes to make the tool function the way it does. So what exactly happens when a user interacts with the tool? Let's say you click to select a chart. This then sends a post request via Django to query our database. There are some parameters encoded in the request, obviously, to make sure we retrieve the correct bit of data that we need. This then gets passed back to the front end, which we then process and use to build the visualizations. And so this is where the D3 magic kicks in. So as I mentioned earlier, D3 builds visualizations using standard web elements like SVGs. SVGs are particularly good for building really high quality, scalable, and potentially dynamic graphics. And this is obviously very important for us because, as you can see, there is a lot of interactivity built into the tool. So pretty much everything you see in the map visualizations on the front end, this is an SVG based from the hexagons in the map to the grid lines, the legend elements, the pop-ups. These are all SVGs that we combine to build the final visualization. Starting from the legend block, which we generate based on the minimum and maximum value of the data that we fetch. We then draw the grid, the border lines for the neighboring countries. We generate the map, all 1700 hexagons. We draw the grid connection lines and the legend for power flow. We draw the circles for the German hubs and the neighboring countries. Then we add the capacity icons. And finally, we add the marker and the bar in the legend. And this is how the visualization for the very first timestamp of the whole selected period gets rendered. And then when the user clicks to play the map, what happens is we then re-render all of this in real time in your browser. So essentially everything other than the legend block, which is static for the entire time period, everything else gets removed and re-rendered according to the data for every subsequent time step. And the end result is an animation of the map playing, which looks something like this. All right, so that's it for the demonstration of the tool. I thank you all very much for joining us today, and I hand it back to Torsten now.
Yes, thanks, Gier, for your presentation. And thanks to all of you giving us a deep dive into the inner workings of the locational agorameter from the different perspective. And to the audience, in case you have questions to what was said or beyond, please drop your questions into the Q&A section, of Zoom. There are already some questions in there that we are going to answer soon. Yeah, the idea behind today's webinar is to shed light on how the results were generated. I hope this was successful so far. We will see with your questions. And to make the process of generating the electricity prices more transparent and easier to understand for both our current audience here and for future users of the locational agorameter. We believe that understanding locational electricity prices can play a key role in better aligning the power market and the electricity grid. This, in turn, can help unlock savings in 3 important areas: expanding renewables, reducing the need for backup capacity, and making smarter use of the grid. Overall, we believe we can reduce cost as we continue to develop our electricity system, and electricity consumers stand to benefit from these savings. With that in mind, we are excited to see growing interest in the tool and look forward to your questions, which we will be answering together now in the panel. And I ask my colleague Katharina Hartz from the German Power team, Kaspar Knorr, one of the core developers of the locational agorameter from Fraunhofer IEE, as well as his colleague Jakob Kopiste, also the big brain after the locational price calculations, and my colleague Gia Loy from the data and modeling team, which she was responsible for especially developing the front end of the locational agorameter. Great to have you here. And now let's maybe start with a very technical question regarding negative prices to the colleagues from Fraunhofer. And the question is, does the locational agorameter also show the strongly negative electricity prices resulting from the marketing of the TSOs? Because the TSO needs to sell the renewable electricity and so accept every price. And the question is, so can we see prices below, let's say, 200 euros per megawatt hour in the locational agorameter? And maybe you could explain a little bit on the price calculation mechanism in the locational agorameter. Is it Jakob or Kaspar who would like to answer this question?
I think that's definitely Jakob.
Yeah, I can talk a little bit about the price formation when it comes to curtailment of renewable energies. Essentially, the negative prices that we do see as part of our models are based on a bit of a simplified approach where we calculate the market premium payments for specific wind farms or solar farms for all of our hubs. And the price that, well, the market premium payments are, first of all, they are based on the result of the EEG auction, depending on the bid of the specific wind farm or operator, minus the monthly market value for that specific technology. And the bid or the price at which curtailment of these renewable energies happens is basically the negative value of the market premium payments. And we do see, especially in the north, especially in the northeast, times where we do have a significant amount of curtailment of renewable energies, where we see very, very negative values there. So that's the basic approach.
Yeah, thanks a lot. And maybe an additional questions regarding the electricity prices. One question is about the electricity prices in the 22 hubs. And it was recognized that it can be that the prices in these 22 zones or in the nodes, so we call it hubs, show lower prices than the average electricity price in Germany. So how can this happen? I guess this is also a question to you, Jakob. So how can it be that the 22 prices are lower than the average price for Germany? Or Kasper, I see you unmute.
Yes, I think it's a question to your colleagues from Agora, but I suppose that the value shown, the average value for Germany is obtained from NSOE, right? For the current market design.
Yes.
So that's the reason.
That's the one reason, and the other reason could, of course, be we have an optimization and regarding the grids with and a difference in the comparing the two systems. The one system does not include the grid because we have the redispatch cost coming on top, and in our modeling in the locational agorameter, we have the grid and the capacity of the grids directly connected in the modeling of the electricity prices. And in an overall European model, this can lead to lower prices for Germany, I think. Yeah. So be aware of these different kind of numbers that you compare. It's always good to see how this to compare things that are really similar, and do not forget about things that are maybe not included in the modeling. Then a question to the quality of the model before we come to maybe more questions about development of the tool. How large are the differences between the live data and the recalculation data?
So what we call recalculation, we do at the beginning of each year for the last year. So
in calibrating, I think the question goes into the direction of calibration of the tool. So have you checked back on backward calculation, how good is your model to meet the average electricity price from the EPEX market today?
Yes, we did for the years 2019 to 2023.
And what was the result?
Jakob?
Overall, we were able to match the historic electricity prices pretty well. As with any modeling approach, it's never going to be 100% accurate. There's always going to be some level of uncertainty there, especially when it comes to price peaks. But as a whole, we were quite happy with how well we were able to describe the current electricity markets for the last 5 years.
Yeah, so that means that probably also the calculation you do now comes to a good result, right? Unless anything changed in the electricity market that is not reflected in the tool, which of course happens sometime. And this is why we also do some recalculation, as you mentioned in your presentation, Kasper, right? So that data is corrected after a year has passed. So in the beginning of each new year, we do the recalculation of the locational prices. One more question to the data. How do you optimize the input data? As I understood, there are more than 35,000 time series in hourly resolution, so it's quite a big amount of data. So I guess people outside are interested, how do you deal with this big amount of data, and how do you optimize the data input?
Yes, it's true. We have more than 35,000 input time series. but they only cover a short period of time. So it's the last 3 days and the next 3 days. So it's not huge data set regarding the large of the data size of the data set. And we use Python and MATLAB environments for this data handling.
Okay, maybe there are more detailed questions, then please drop it to the Q&A section, and we can make sure to answer these questions as well. With that, leading more to the development of the front end of the Agorameter GIA. One question is, how did you decide on the colors for the visualization of the Agorameter?
So for the colors, a lot of this is actually based on our existing corporate design, which was developed by our wonderful colleagues on the communications team. So we've got specific colors that we use already for certain energy-related concepts, like a green and a gray that we use for renewables, and there's a specific shade of maroon for emissions and things like that. And you can actually already see these colors in the live Agorameter in the charts. So for the maps, we could reuse quite a lot of these color concepts. For example, if you look at the renewables map, it's got a similar theme of green and gray, and the emissions chart also use a maroon kind of theme. So this creates some kind of a nice continuity between the live and the locational Agorameter. And then we had to develop some new color schemes, for instance, for price. So we decided to go with some colors that made sense in the context of price, like higher prices are red, lower prices are green. Negative prices, which are not necessarily good or bad, are gray, because we do want to highlight that they are different from positive prices.
Mm-hmm. So, and since the visualizations, we got very good comments to the visualization we have done so far, especially comparing to other locational price systems. I heard that you did a good job, Gia. So the question is, when I would like to use these figures in my presentation, how can I download this animation of the map in a playing way so that I see the animation?
Okay, so there are so to download actually the animation from the tool itself, this is not currently possible because of the way the SVG elements are rendered on the fly for each timestamp. So they're not actually stored anywhere. So I would recommend, depending on your use case, you could either just share the link to whatever map. The URL always includes the date range, so whoever gets the link will be able to see the animation playing. Otherwise, there are some workarounds to actually get a playable image. So one thing you could do is, for instance, take a video of your screen when it's playing and convert the output to a GIF, for example. Or better yet, for smaller time ranges, you should maybe use the screenshot option, which provides some really high quality images, and then combine these together to form a video output. But then I would only recommend this for smaller time ranges, because otherwise you would have to download multiple screenshots.
Yeah, thanks for the explanation, Gia. And since my last question was a little bit, or was quite positive, maybe a little bit more critical question. Were there any significant challenges in developing the tool?
Yes, there were many challenges in developing the tool. But I would say quite a big one was maybe integrating it with the existing Agorameter, because so this is, as you can imagine, we already had a live Agorameter, and we had to integrate what we were building in the locational Agorameter into this tool. So this is quite different from building an entire tool from scratch, where you've got full control over the development of the existing environment and so on. So we had an existing technical infrastructure that we had to work with, and we had to make sure at every step of development, what we were developing was compatible with what we already had previously. So I'd say that was one technical challenge. A maybe not so technical challenge was that this was a really big project that had a lot of moving parts to it. So we were just building the tool, but then obviously there's a whole study of which the tool is only a small part. And then there's a model which produces the data behind the tool. So basically this required a lot of interfacing, a lot of coordination between different groups of people. So I think it was a really big effort for everything to come together.
Yeah, thanks, Gia. Really a big effort for everyone involved. And so maybe, Katharina, the question comes to you. How do you envisage the tool being used, and what are use cases you have in mind?
Yeah, good question. Putting myself in the shoes of different users. Well, maybe I can think of 3 ways to use it. One, of course, is also one of the main ways we intended it to be used, which is understanding the topic a bit better. I think what this tool can do better than any study is really giving users the opportunity to discover the impacts of local pricing themselves in a way that is maybe more comprehensible than 100 pages of text. And really understanding that that there could be another dimension to the power price, which is location. Because in the large German bidding zone where we're sitting now, this is difficult to notice, but in Sweden, for example, or in Italy, this is something that people have already understood. And beyond that, not only understanding that there is or there could be this dimension to the power price, but also understanding the links and relationships between the price, the generation, demand, and grid capacity. Then another use case that I could think of is, of course, forming an opinion on based on my personal interests. For example, if I want to invest in a large consumer, I could use the tool to see if it makes sense, or at least get an idea of where it would make most sense. And then maybe the use case that I will see, or I will use most for myself is using the data for further research and answering maybe questions from the system perspective, and doing more analysis on that.
Yeah, thanks for highlighting these different use cases, and maybe there are more around. So let us know what you do with the data, please. And there are some questions in the Q&A section regarding, hey, is this data available? Can you do this with the tool? And as I saw, some are not able yet to do so. What are the further developments you see, Katharina? Also, there was a question on the market value of renewable energy. Will it be shown in individual zones? So could you say how would be the further development of the locational agorameter?
Yes, we of course want it to be relevant beyond its publication date. So we will develop it further. I think we did try to make everything that we could think of and that was possible to develop available now. So maybe we cannot come up with more features tomorrow, but we will definitely keep on developing as also the debate develops. So we are very grateful for any hints and ideas that you could forward to us, either via the usual contact points, mail, and also the ones that Maxi posted in the chat, but also via a feature that is new to the whole Agorameter family, the feedback and the changelog that you can use to see what is new, and based on that, maybe come up with more ideas on what could be new.
Yeah, and maybe there are others developing similar tools as it was done with the Agorameter. There are several other tools in the market available that yeah, started with the same idea as the Agorameter did, and yeah, put much more functionality to it than we have actually in the Agorameter. And maybe exactly this can happen also with the further discussion on locational prices. We hope to inform this discussion, and that was done with all of you here and lots of people behind the scene that are not present yet in this webinar. So thanks a lot to you for your questions, and also for the hard work you spent to make this new locational Agorameter live. Also special thanks to Norman Gerhard from Fraunhofer IEE, who was one of the brains behind the locational Agorameter idea in the beginning and helped a lot to make it reality.